Okay, for number 1, a covalent bond occurs when 2 nonmetals, okay, it has to be 2 nonmetals, share electrons, right? To what? What are they trying to do? Fill the what? Yeah, outer shell or the valence shell. Either way you want to put that. Works. Okay? Okay, first name. Angelina. F2, polar, nonpolar, or ionic? Nonpolar. We have a difference. 4.0 minus 4.0 gives me a 0, which is nonpolar. Next. Okay. I have a 2.8 minus a 2.1 gives me a 0.7. What is that, Leighton? No, it's a polar. Anything above a 0.4 to a 1.7 would be polar. Continue. Next. Okay, 4.0 minus 1.0 is 3.0, which is an ionic bond. So we were just looking for the differences between them. Okay, number 3, what difference, Raymond? How big? How big? Larger than 1.7, right? Greater than 1.7. Whereas a smaller difference, shall we say, yeah, less than 1.7. Okay? So we're just trying to find the dividing line. It's not a perfect dividing line. There's little gray areas. We'll talk about some of those later on down the road. We're just trying to generally say in that area is where we start seeing some of those properties change. In that area. Okay. This is the area that for some of you is probably the hardest. So CBr4 would be a carbon with 4 bromines attached. It is an AB4 type of molecule. AB4, right? A central atom and 4 bonded atoms. Who's up? Dante, do you have any idea what shape it would be? Tetrahedral. Okay? Tetrahedral. Good. And the good thing about matching is you just have to be able to recognize it, right? Okay? Hang on. Dante, do you know the name of CBr4? Anybody want to give me the name? Yes. Carbon tetrabromide. Now, in the review, there isn't a whole lot of questions on names and formulas. There's not a whole lot of questions on the test either. But you need to be able to name that. Polar or non-polar? Next person. Okay. 2.8 minus 2.5 gives me a 0.3. So what is that, Adam? Pardon? Non-polar. And the molecule, Adam, is it polar or non-polar? The molecule. It is non-polar. So, we have an example here. I know it's kind of difficult to see. It's a tetrahedral carbon tetrabromide. The carbon in the middle is the least electronegative, so they're all tugging at its electrons, trying to attract its electrons, but they all pull equally. So if they all have the same pull on them, nobody is getting more than the rest of them, so it's a non-polar molecule. As long as they're all pulling equally, it's going to end up being nonpolar. Okay, who's up next? Okay, shake. Okay, this is the one that I saw when I was grading. That is correct. Incorrect. Wow. Trigonal, pyramidal. When I was going through the labs, a lot of you are writing trigonal planar. It's pyramidal, yes. It is crazy. Yes. So you can see right here, this lone pair pushes down on the other electrons, which creates a small pyramid. If this lone pair wasn't here, it would be flat. But the repulsion pushes these down, which raises that central atom up, which creates a three-sided pyramid. So that lone pair is what does that. Okay? The name, Adam. Oh, who's doing it? Whose turn was it? Brando, what's the name? Phosphorus trichloride. You need to know the prefixes. Mono, di, tri, tetra, penta, hexa. If you know those 6, you should be okay. And again, you just need to mostly be able to recognize them. Yes, ma'am. So your N is 4 times 8, which is 32. Each chlorine has 7. 7 times 3 is 21. Plus 5 is 26. So they're going to share 6 electrons. 2, 4, 6. Okay? You okay with that? And then 26 minus 6 gives me 20 unshared. So I'd go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Are you okay? Good question. Did you miss somewhere? Are you okay? Okay. Next, who's up? Okay, Hector. 0.9 difference. The bond is polar, and again, we're talking about just the bond between the phosphorus and the chlorine. We're talking about a single bond. A lot of you are trying to add all these up and subtract just the one. We're only talking about a singular bond here. And is the molecule polar or nonpolar? Polar. Why? No, because they each have. But the lone pair we talked about before, the lone pair alone will make a molecule polar. It has an easy way to recognize a 1 or 2 lone pairs. That's what this little brown thing stands for, the lone pair of electrons. This makes us very, very, very negative up here. There's just electrons out here, out on their own. Okay, so anytime you see 1 or 2 lone pairs on the central atom, not on the ones on the outside, on the central atom. Okay, H2O. What do we got? Who's up? What's the shape? Nope. Bent or angular? Yes. The 2 lone pairs. If you looked at this straight up and down, you might guess that it's linear. But because of these lone pairs, it becomes bent. These push down, giving it more of a 3-dimensional shape. So the name on that? hydrogen monoxide. Okay, and we have a difference of 1.4, so that's what? Polar. And the molecule, Heather? Polar. In fact, it's got 2 lone pairs, which makes it even more polar. Okay, SiO2, who's up? What's the shape? Okay, linear. Right. That's our molecule right there. The name? Silicon dioxide. And the difference, we have 3.5 minus 1.8 gives us 1.7, which makes it very what? Yeah, very polar. It's right on that dividing line. Okay? Right on that dividing line. And the molecule itself? So tell me which side wins if it's polar. Which one of these is pulling harder than the others? Non-polar, right? So again, you can have, when we say it's a polar bond, we're talking about just between the silicone and the oxygen. That is polar. But overall, both of these ends are identical, so neither side is going to share those electrons more than the other side. So the molecule becomes nonpolar. Okay. And number 5, who's up? Try again. Eight. Got it? How many double bonds? 1. How many triple bonds? 0. A single bond is how many pairs? 1. A double bond? Triple bond? 3. Okay?